Alright, in that last video I did the overview of the sort of the control block diagram, and then I did a sort of a 1D first order system where it was translational. So there was a car with thrust and then drag. In this example I'm going to do a rotational problem. This problem is actually going to turn out to be second order as well, and in terms of the differential equation that's going to be created, but basically we're going to use Newton's extension, which is typically called Newton-Euler equations of motion, to do the rotational dynamics. And I'm going to do a satellite in space. It's going to be 2D. So I've got my spacecraft here, I've got thrusters on either side, and I can apply some force Fc, and I assume that there's a thruster on the other side. So thrusters are always positive. If you had negative thrust, that would be like a vacuum. And so if you want to apply a moment this way, you turn this thruster on, and if you want to rotate the other way, you turn that thruster on. But as far as the control system is concerned, Fc can be positive or negative. Which thruster you turn on depends on the mechanics of the thrusters, which is not what we're going to look at today. Okay, so in order to get this fully defined, what I need to do is I need to establish an inertial frame. So I'm going to call this point, this inertial point I. This is the x-axis, or the y-axis is the x-axis, and so positive rotation is this way. And so then I put a frame here that is fully aligned with the spacecraft, and so this x-axis rotates with the spacecraft and is always pointing out the nose of the spacecraft. And then the angle between the inertial frame and the body frame, I call that theta. The big black, like I guess it's black and white, it kind of looks like a yin and yang. That is the center of mass there. And the distance from the center of mass to the rotation point, I'm calling that d. If you recall from dynamics, if you want to rotate a system, if you apply a force right through the CG, it won't rotate it. You have to apply an offset. So that distance is called d. Okay, and that's basically everything that we need to get the equations of motion. And again, this is a free body diagram. And by the way, the steps to sort of answer a control problem is step 1, free body diagram, step 2, equations of motion. Step 3 will come in later chapters, but basically that's going to be, open loop dynamics, and then step 4 will be closed loop dynamics and control design. And so we're just doing step 1 and step 2 right now, free body diagram, equations of motion. So since the system is rotating, you have to use the Newton-Euler equations of motion. And the Newton-Euler equations of motion are very similar to Newton's second law. If you recall, Newton's second law is sum of the forces is mass times acceleration. Well, Newton-Euler equations of motion are sum of the moments, this is the moments, is equal to the moment of inertia times the angular acceleration. So it's very, very similar to the version before. And if you look here, I'm saying that the rotational inertia of this spacecraft is J. Okay? So now let's look at the left-hand side. So the left-hand side, because I'm in space, I'm in deep space, there's no aerodynamic drag. You could technically argue that there's a little bit of aerodynamic drag, but it's like 10 to the minus 6, and then you could argue that there's radiation pressure, which is like 10 to the minus 9, but those things are so small, I'm just going to ignore them. So I'm going to say that the total moments on the spacecraft is just the force times the distance. That's what moments are defined as, is force times distance. And then my angular acceleration is just the second derivative of my angle, and so I'm going to call that theta del dot. So if I take this equation and rewrite it, and then plug everything in, I'm going to get Fc times d on the left, and I'm going to get j theta double dot. I box this equation because these are my equations of motion. This is a differential equation, it's second order, there's two derivatives, and I've got my force input Fc. Now, if you were in dynamics, you would go here and stop, but let's connect this back to control system. So if I was looking at the open loop system, my plant, G, is described by these equations of motion, where my input is a force Fc from the thruster, and my output is the angle of the spacecraft. And so if I apply a force, the system will rotate. If I don't apply a force, then the system will just stay there. And then G is my transfer function that relates output over input. And so this is my transfer function that I can create, and again, we're going to do that in later chapters. But this basically describes output over input, which comes from these equations of motion here. Very, very simple problem. Hope you enjoyed this video.